Last time we'd introduced Rolle's theorem and the mean value theorem. And so the mean value theorem is a really important theoretical tool because it's going to give us connections about the value of a function on an interval with the value of its derivative. And this connection allows us to interchange the two. And that becomes really important as we go on and develop applications. And why do we care? Well, the first thing that we are going to use the mean value theorem for is to understand what the derivatives of a function tell us about the shape of that function. And so we're going to develop this idea by working with an example today. But first we'll dive into this. So let's talk about the first derivative. So we've got a function and we're supposing that we've got its derivative. So we'll make an assumption here. So we'll suppose that f prime is positive on some interval a to b, and we'll take it to be an open interval. So we'll choose any 2 points in there. So we'll let x1 and x2 be in this interval a, b. By this assumption, so we are assuming that f prime is positive. So by the assumption, that means f prime exists on whatever interval we've got, x1, x2. And that means that f is going to be differentiable on that x1 and x2. And since f prime exists on the full interval, that means f is continuous on that full interval. So over here, we've got that our function is continuous on any subinterval we want. Because it's going to be continuous on this full round interval, we can take it to be continuous on a square interval however we'd like. So this will be continuous on square interval x1, x2, and that means that the mean value theorem applies on this interval x1, x2. And that means there has to be a point, some point between the x1 and the x2, where f of x2 minus f of x1 over x2 minus x1, this thing has to be equal to some f prime of c. Now, the key idea here is that we are assuming the function is positive in terms of its derivative. So because of that, we know that this is positive. Breaking this down even further, we know that this is positive because x2 is greater than x1. And the only way that this fraction will end up being a positive number is by having the numerator be positive. So that result right there, this implies that f of x2 minus f of x1 has to be positive on our interval x1 to x2. And that means f of x2 has to be bigger than f of x1 on that interval. And this has to be true for any x1 and x2, because we just picked x1 and x2 to be some arbitrary numbers. So by definition, you may or may not remember this from your pre-calc class, this means that the function f is increasing on this x1, x2. So because x1 and x2 were arbitrary, this implies that f is increasing on this interval a to b. Now, I could also show this converse of this. F increasing means that f prime is positive. And I could also show that the function decreasing has a two-way relationship, that if a function is decreasing, it must have a negative derivative and vice versa. But here, just to summarize it, is the point of all of this. From the mean value theorem, we have just shown that if a function has a positive derivative, that will mean that the function has to be going up. Now, again, I said without proof that we could go the other way. If a function is going up, there's no choice but for the derivative to be positive. And similarly, if a function has a negative derivative, the function must be going down. And if the function is going down, it has no choice but to have a negative derivative. Now, that is really important information. It agrees with what we expect in terms of common sense, right? As we walk from left to right, we expect that kind of behavior. Positive tangent line slopes when functions go up, and negative tangent line slopes when functions go down. But it's nice and it's reassuring to have the mean value theorem be able to tell this to us. So this leads to a simple way of figuring out relative minima and maxima. So it leads to a test for finding relative minima and maxima. And that was kind of what our ultimate goal is in chapter 4. We want to be able to figure out how or where a function has its high points and low points. And it doesn't have to be absolute. Any local one will do. So this is something called the first derivative test. And it reads like this. If C is a critical number of the function. Now, critical number is important. It means it's a point in the domain of the function where the derivative is 0 or the derivative doesn't exist. So if C is a critical number of your function, then you get one of these options. If f prime changes sign from positive to negative across x equals c, then x equals c is what we'll call a local minimum. And think about the graph, right? If a graph has a positive derivative, it's going up. And if it has a negative derivative, it's going down. So somewhere right there, something has to happen. Either derivative is 0 or the derivative doesn't exist, but it's a local high point. Now, similarly, if f prime changes sign from negative to positive across x equals c, then we'll say that x equals c is a local, up here I wrote min when it should be max. A local maximum, my mistake. And here, when f prime changes sign from negative, which means the function is going down, to positive, which means the function is going up, that's what we talked about with the mean value theorem, that means we have to have a local min at x equals c. Now, that all seems very reasonable, but there's one last case that's important here. If you look at these first two items, they're both about f prime and the sign change of f prime. So if f prime does not change sign, then you don't have anything. We have no local extremum. There are going to be situations where a function doesn't change its derivative value. So for example, a cube root function is going up, it's increasing. At 0, it has a vertical tangent line, but as we continue through 0, it still increases. Because there's not a sign change, f prime is going to be positive in both cases. There is no local minimum or maximum. Now, it's important that it's a critical number. Critical number means point in the domain. And the other condition that we're going to be talking about here is that there has to be a function that is continuous. So I forgot to mention that here. We are also going to assume that the function is continuous. Why do we need that? Because we don't want bizarre things like this happening, where we've got these strange behaviors. We want functions that are continuous at points like this. Here we would say that, oh, the function is decreasing and then decreasing again. We don't want any strange things happening like this. When you put all of this together, you'll have a very reliable way. So again, it's important that the function is continuous on this interval. The example that I'm going to work with in this video and in the next one is the function x squared over x squared plus 3. You could simply use the quotient rule or the chain rule, however you'd like. You could figure out very straightforwardly that its derivative is x squared plus 3 squared. This function is a rational function. It's continuous everywhere because the denominator of this function can never be 0. We've factored the function f prime here. We could say very easily that f prime equals 0 at x equals 0, and f prime always exists. There are no points in the domain of this function where f prime does not exist. The denominator can never be 0 here. So this is the only critical point. Now, it's going to be really important for us to have a reliable way of determining the signs of f prime. So we are going to build sign tables. This is used for us to evaluate the sign behavior of f prime. On the sign table, here's how it's going to work. We are going to put two key pieces of information. Up top, we are going to list the critical numbers. So we put all the critical numbers in increasing order up top. This function only has one. So essentially, we're taking a number line and we are splitting it up, partitioning it according to the critical numbers. Now, on the other side, we are going to put the factors of f prime. So the factors of f prime are going to go there. The reason we want factors is because it's easy to figure out how a function behaves or what its sign is based on its factors, because the sign of a function just depends on multiplying pluses and minuses, and that's what we're aiming to do. So this derivative only has two factors for us to worry about. It's got a 6x in the numerator. X squared plus 3 squared could be written and left as is. And so what we now do is we go through this sign table and figure out the sign of each one of these factors. So for instance, x squared plus 3 is always going to be positive no matter where you put it. Any value of x you put into there will always give a positive result. But if you pick values of x that are less than 0, like -10, 6 times -10 will be a negative number. Whereas if you pick a value of x greater than 0, like 1,000, 6 times 1,000 will be a positive number. Now, you're going to spend a lot of time and effort factoring f prime so that you can build a table like this. And once you've factored it, it's a simple matter to figure out what its overall sign is. So for instance, in this case, you're just dividing the two signs. This will tell you that f prime is negative here, and it will tell you that f prime is positive there. This is a critical number, and f is continuous at x equals 0. So this is a point on the graph. It's in the domain. That point will now be under consideration. This is telling me that the function f is decreasing from -infinity to 0 with a round bracket. That's what the negative in the derivative means. Whereas up here, f is increasing on the interval round bracket 0 to infinity. That's what the positive in the derivative means. So you've got a function. You don't really know what its picture looks like, but what you figured out is that everywhere up to 0, the function is decreasing, and everywhere after 0, the function is increasing. So what that tells you is that by the first derivative test, we have a local minimum at x equals 0. It might be a local, an absolute minimum. And in this case, it's going to turn out that it will be, but the first derivative test can only directly tell you whether they're local or not. And this is how this test works. It's very simple. You take a derivative, you factor the result, and then you build a sign table. Now you have to be careful. You need the function to be continuous at the points you're looking for. So as an example, if I give you the function x to the minus 2, if I take its derivative and I get negative 2x to the negative 3, I might be tempted just to dive right into this process and say, oh, this is what the derivative looks like. F prime of 0 doesn't exist. So you might be saying, oh, okay, I'm going to build the same sign table that I did before. The factors are negative 2 and x cubed. Negative 2 is always negative. X cubed changes sign with x. So when I'm negative less than 0, x cubed is negative. When I'm greater than 0, x cubed is positive. So I might say, oh, look, f prime is positive and f prime is negative. So you might be tempted again to say, look, oh, okay, the function's going up and then the function's going down. So do I have a local maximum at x equals 0? And the answer is no, I do not. And the reason I do not is that the function is 1 over x squared. It is not continuous at x equals 0. So the function is not continuous at x equals 0. It's not even defined. The graph of the function is just kind of what I call a volcano. There is nothing happening at x equals 0 except a vertical asymptote. There is no local max. There's no absolute max to this function. So it's really, really important that the function you're dealing with is continuous at all of those critical points in order for you to be able to use this first derivative test to figure out local minima and maxima. Now we're going to use a similar process to tell us more in a sense that's related to